Have you ever just looked around and wondered why everything is so different? Why some things are shiny, some are strong, and others just kind of fall apart? Well, today we're going to crack the chemical code that separates all these materials. Let's dive in. So let's start with a really simple everyday mystery. You've got an iron nail, leave it outside, and you know what happens. It turns into this flaky orange mess. It just rusts away. But then you have a gold ring. It can be passed down for 100 years and it still shines. Why? What is going on there? I mean, these two metals are playing by totally different rules. Iron is our workhorse, right? It's strong, it's super useful, but it breaks down. Gold, on the other hand, is actually pretty soft and it's rare, but it seems to last forever. To understand why, we need to figure out what those rules are. Okay, so to start our investigation, let's look at the obvious stuff, the physical properties we all kind of remember from science class. These are the classic clues we use to identify a metal in a lineup. First up, you've got malleability. This is that awesome property that lets you hammer a metal into a super thin sheet without it shattering. It's why you can have gold leaf so thin you can practically see through it. And then there's its cousin, ductility. This is the ability to be stretched out into a thin wire. This is the whole reason we have copper wires carrying electricity all through our homes. And just how far can you take this? Well, gold is basically the world champion of ductility. Get this, a single gram of gold, weighing less than a paperclip, can be drawn out into a wire that's 2 kilometers long. That's just mind-blowing. And of course, there are the other classic traits. Metals usually have that metallic luster, that special shine. They're great conductors of heat and electricity. Think of your cooking pans. And they're usually hard, solid things that are sonorous. They make a ringing sound when you hit them, like a bell. So case closed, right? Well, not so fast.
Because this is where our nice, neat story gets a really interesting plot twist. It turns out that if you rely only on these physical clues, you're going to get into trouble.
And this is the key takeaway. You just can't group elements by how they look and feel because there are way too many exceptions to the rules. The real world is just messier than that.
And check out these rule breakers. Mercury is a metal, but it's a liquid. Sodium is a metal, but it's so soft you can literally cut it with a dinner knife. Gallium and cesium are metals that will melt in the palm of your hand. And then you have graphite, the stuff in your pencil, which is a non-metal, but it conducts electricity. These exceptions tell us we've been looking in the wrong place.
So, if the physical clues aren't the answer, what is? Well, that deeper look brings us to the real secret, the chemical master key to understanding everything.
So, this is the big question, right? If you can't trust what an element looks or feels like, how do you really know what it's going to do? How can you predict its behavior?
And the answer is actually really profound. It's not about what they look like. It's about how they react. An element's true nature, its real identity, comes out when it interacts with other things. And here it is. This is the master key, the reactivity series. Think of it like a power ranking for metals. At the very top, you've got the super aggressive ones, like potassium, which basically explodes in water. And then you go all the way down to the bottom, where you find the really chill, unbothered ones, like gold. This list, this simple ranking, explains almost everything. So now that we have this code, we can see how it predicts what happens in the real world, from how we get metal out of a rock all the way to how we build something like a railway. And here's the #1 rule of this game. Any metal on this list can basically kick out a metal below it from a chemical compound and take its place. It's a power struggle. The more reactive metal always wins. It's called a displacement reaction. And this idea is so important that it actually dictates how we get metals in the first place. The whole science of pulling pure metals out of the earth, it's called metallurgy. And the strategy you use depends entirely on where that metal sits on the reactivity series. So here's the playbook. For the lazy metals at the bottom, like mercury, you pretty much just have to heat up their ore. Simple. For the guys in the middle, like iron, it's a bit more work. You have to roast them and then use carbon to pull the oxygen away. But for the super reactive ones at the top, like aluminum, they cling to oxygen so tightly that you need to use the brute force of electricity, electrolysis, to rip them apart. And if you want to see a really dramatic example, look no further than the thermite reaction. Here, you use super reactive aluminum to rip the oxygen away from iron oxide. The reaction is so intense, so energetic, that it produces molten iron on the spot, hot enough to weld giant steel railway tracks together. That's a perfect display of reactivity in action.
And this is where it all comes together. Understanding this chemical code isn't just for a textbook. It lets us actually control and engineer materials to build a better world.
Let's go all the way back to that rusty nail from the beginning. This classic experiment shows us that iron only rusts if it has two things, air and water. It's a chemical reaction, and because we now understand the chemistry, we know exactly how to stop it.
And one of the cleverest ways we stop it is by making an alloy. An alloy is just a fancy word for a mixture. You take a metal, you mix in some other elements, and you create a brand new material with way better properties, like making iron that won't rust. You know, this isn't even a new idea. This is the famous iron pillar of Delhi. It was made 1600 years ago, and it's barely rusted at all. It is an absolutely incredible piece of ancient engineering made by people who had a deep, intuitive understanding of how to control the elements. So that leaves us with a final thought. We started out looking at the shiny surface of things, but we found the real answers hidden in their chemical code. By understanding that reactivity series, we can not only explain why a gold ring lasts forever, but we can design new materials ourselves. So the question is, now that we've cracked the code, what are we going to build next?